This conference will now be recorded.
All right, thank you everybody for joining us for another Grasshopper session. I mean, we had 5 last year. It was a pretty good progression. I think we all learned a lot, and it's great to have the recordings and go back to them. And so now this year we're looking ahead, trying to think about what we're going to do for the next session, next series of sessions. And something that me and Tom have always been talking about is really bringing in Bohan, because Bohan's really been working with a lot of scripting, especially on the environmental side on a per project basis. And I think he has a lot of experience that we want him to sort of share with us. And he's developed a pretty solid set of scripts. And we're sort of trying to brand this. I think Kristen has talked about branding this as the hyper group, as a sort of high performance group, people that are interested in making high performance buildings and talking about what it takes to get to that discussion. And so, everyone here in the Grasshopper group, I think there's a little bit of an overlap because, we're also looking in that same space, maybe in a lot of different disciplines, but also specifically for high performance buildings. So I guess I'll pass it over to Bohan and you can take it away and tell us all about it.
Thank you. So we are a team working on the project in a way to measure, analyze, and track the energy usage and building performance. So today I'm glad to share some of our study, specifically the day-night study. So we know that, so why we are studying day-night, we know that 40% of the total energy consumption goes into the building sector in the US. And in the buildings, almost 25% of electricity is used by the electric lighting. So it is a worthwhile endeavor to maximize the usage of natural light and increase the efficiency of electric light. And for many of you may know or don't know that we can use illuminance as an indicator of the quality of daylight. So illuminance is the density of luminous power per area, and the unit of that is lux. So 1 lux is the light that is cast onto a 1 meter by 1 meter surface from a candle that is put 1 meter away from that surface. So the illuminance is put in time measurement of daylight. But for the annual daylight study, and we know that there are 8,760 hours in a year, and the occupancy hours are different based on different building types. So we are using 2 concepts to measure the annual daylight. The one is the daylight autonomy. So daylight autonomy is the percentage of occupancy hours within a year, which illuminance is greater than 300 lux. So as you can see from the graph on the left, this is a result from our annual daylight analysis. And this legend shows the range of the daylight autonomy. So the red and the yellow color and is indicate that the daylight autonomy is above 50%, means that these areas, these yellow and red color areas, receive daylight that is greater than 300 lux for more than 50% of the year. And we consider these areas have sufficient daylight. So if you want to further quantify what is the percentage of these red and yellow areas of the total areas on this floor that we are analyzing. So that is the concept of spatial daylight autonomy. So spatial daylight autonomy is the percentage of areas that receive sufficient daylight in a year. So daylight autonomy is the percentage of time, and this is the percentage of area. And so for annual daylight simulation, I divided the workflow into 3 steps. So the first step is building the geometry. So we will start from the first step. So this is the geometry that I prepared for the daylight simulation. So to conduct the energy simulation, in this case, the daylight simulation, we want the geometry to represent the design of the building, but in a simplified way. So I will show you what I have built in this model. So first I built the interior building volume. You can also call it the building zone of this floor. So the concept of building zone is that it is the space that people occupy on this floor. So you can also think it as the space that is covered by the building envelope. And another important geometry is in the model is the vision glazing. So as we know, the vision glazing are the geometry in the model that is transparent. So it is the geometry that allows daylight goes into the space. And apart from the glazing, these are the opaque geometry that in the model. So the interior wall, the exterior wall, and the window frames. So these are the opaque geometries that block the daylight. So after I have built these geometries in the Rhino, I can link this geometry into the Grasshopper. So what we can do is we can create a geometry component in the Grasshopper and use the set one geometry or set multiple geometries. For example, if I want to input all the exterior wall into the Grasshopper, I can select the walls in the Rhino and right-click the geometry component and set multiple geometries. And now all the exterior walls are linked into the geometry component in the Grasshopper. So here I have linked the interior building volume, the glazing surfaces, interior walls, the window frames, and the exterior walls in the Grasshopper. Another important thing that we should pay attention to is that we need a test surface for the daylight simulation. So the test surface is the surface that actually receive the daylight in the building volume. So normally we create the test surface at the table height. So and also the test surface should include all the areas that I'm interested in to conduct the daylight simulation. So in this case, I'm modeling the whole floor area as to be the test surface. But if you are only interested in, for example, this small area, you only need to model this area. You don't have to do the whole floor. It's based on what you need for the analysis. And I also link the test surface in the Grasshopper. So first, there are several components that transform our geometry into the zone that has the building information. For example, first I pass this interior building volume component to this honeybee component called the master zone. So what this component does, it transforms this zone geometry into a geometry that has the information of this building. So to make this more clear, we can use a panel to say what it is. So if I link a panel to the zone geometry, it only has the information of the geometry itself. But if I plug this into the panel, we can say after this geometry is passed through this mask to zone component, by default, this component gives a function to this geometry. Now it is an open office, and this space is conditioned. So if you recall that we say for the daylight autonomy, we are interested in the percentage of time of the occupancy hours. So after this geometry has been assigned with an office function, so later for the daylight simulation, the Grasshopper will know that this is an office and the occupancy hours for this office is from 8 a.m. to 5 p.m. And you can also change the program by plugging some more information here, the zone program. And if you are simulating, for example, if you are doing an energy simulation, you want to do this for the passive house, you don't want the space to be conditioned. You can also do take the function here to turn off the condition in this space. And after that, there are two components here. What they do is they add the glazing to this zone geometry and decompose the geometry into different building categories. So if I turn off the building volume, so now you can see when I pass the zone to these two components here, now the Grasshopper knows that this is the opaque wall on the facade, and this is the ceiling. This is the floor, and this is the Bayesian glazing. So in this way, our zone geometry is decomposed into different categories of building components for us to further modify them. And the one thing to notify is that we still don't have the interior wall, and we don't have the exterior wall and the window frame. That is because these geometries are not generated automatically from the zone geometry. So we need to assign them separately. So for example, here I connected the interior wall to a separate honeybee surfaces. And as for the exterior wall and the window frame, because they are outside the zone, so I treated them as the shading elements which block the daylight. So I pass these two geometries. I pass these two categories of geometries to a component called honeybee context surface. So in this way, these two layers of geometries are treated as the shading elements in the daylight simulation, which will block the daylight. So now we have successfully created and separated the building geometry into different categories. And the next thing that we need to do is we need to give each geometry a value for their for the material. So as we know that for the transparent material, we need to give it a transmittance. So transmittance is the amount of light that goes through the glazing when it hits the window. And for the opaque building elements, for example, the floor, the ceiling, the wall, we need to give them a reflectance. So reflectance is the amount of light that is being reflected when it hits these opaque surfaces. So this value is the value that you can find from the product information from the manufacturer, and this value is something that vary from project to project, and you need to change these values based on your design. And now we have prepared all the geometry that is needed to do the energy simulation. And the part 2 is the analysis recipe. So to understand what is this, it is something very similar to the recipe when you cook. So this is like the material that we prepared, but only have the materials. We are not able to do a data simulation. We need a recipe to process them. So here there is a component called annual data simulation. It tells us all the recipes that we need to process all the geometries. So the first thing that we need is the project north. So by default, the Grasshopper will think that the top of the screen is the north. But as you can see that for this project, the north is of 45 degrees from the north. So to modify this, we can draw a line that from the origin in Grasshopper with the same direction of the north of our project north, and we can use a component. We can use a vector component in Grasshopper and link this direction into the Grasshopper and plug this into the north, so that the Grasshopper knows our project north. And the second recipe that it asks for is the EPW weather file. There is a component in the Honeybee called Ladybug download EPW weather file. If you put this onto the canvas and you activate this component using a Boolean toggle, a website of EPW map will automatically pump up, and we know that this project is in Boston. So we can type in the city name and search for the location of our project. So now you can see these are the dots of the weather stations that are in Boston. So by clicking on one weather station, and I can copy the link of the URL of this weather station. And if I go back to Grasshopper, I can paste the URL of that weather station onto my Grasshopper canvas and plug this into the weather file URL, so that the Grasshopper knows that where this project is. And the third thing it asks for is the test point. So the test point is generated from the test surface that we just created. So to understand this, if you look at the analysis result on this graph, if you zoom in, you can see these little squares. So this is one grid. And by assigning a grid size here, we are able to generate these equal size small squares on the surface. So the smaller the grid size, the smoother graphic that we could get in the end. And also it takes longer time to run the analysis. So normally the largest grid size should be 24 inches by 24 inches, which is 0.6 meters in our case. And you can make this size smaller if you want to have a better graphic. So after we set up the grid size, so this component will generate this test points on the test surface. So each point will be used as a point to record the value from the daylight simulation. And the last but not the least is it asks for a radiance parameter. So in the radiance parameter, we can define the quality of the simulation that we want. So in this case, we have 3 choices. So 0 means that the low is the quality, and 2 is the highest quality. So we always start from 0 here if we are doing a test. And if we choose 1 or 2, it may take hours to run one analysis. So the other thing is the AB. So AB is the ambient bounces. So here, normally the number for ambient bounces is 4, and you can increase that number. So to clarify what ambient bounces is, here is 2 graphics. So if you look at this section of the room, so let's say if here is a test point, and the light goes this way and this way and this way before it reaches the test point. So in this case, we can see that the light is bounced twice before it reaches this point. So in this case, the ambient bounce is 2. But if you imagine if we are simulating the roller shades behind the window, the light maybe bounces several times before it enters the room. And if the room is deeper than that, it will also increase the number of bounces here. So to be safe, I use 5. And you can also increase these numbers as you need. So now we have set up the recipe for the analysis. And now we have finished the part 2, and we can go to the part 3, run the simulation and interpret the results. So we are using a component called the run daylight simulation component, and we plug the geometry that we created into the honeybee object, and we plug the recipe into the analysis recipe, and by clicking on the Boolean toggle, we are able to run the analysis. So I have run the analysis before this session, and so after the running of the daylight simulation is finished, we can pass this to a read annual simulation component, which extracts the result data from here and process it into the data that we want. So we are interested in the daylight autonomy in our case. As we can see, if I bring a panel here, these are the daylight autonomy that is generated for each and every point. So total there are 1,605 points that we generated from this component. So each point has a daylight autonomy value here. And we can use a component called recolor mesh to plot this result onto the floor plan so that you can see which area reaches the past threshold of 50% daylight autonomy and which area does not pass. And so there are multiple ways to further process this data. So for example, in this case, I can pass the result to several components. So I'm using this component called core faces component, which remove the areas that do not pass the 50% threshold and only select out the area that pass, so that I can get a number that I divided these areas by the area of the whole floor. So I get the percentage of this area that pass the 50% threshold. And also I can pass these areas into several components and to highlight use a thick black line to highlight these areas. And this is something that we can show to the client that we can say on this floor, these are the areas that have sufficient daylight. And these areas are share about 36% of the whole floor area. So based on this workflow, there was a project that I worked on. It is an apartment unit project. So in this project, we are using the annual daylight simulation to simulate the daylight on each apartment unit. So in this case, we started the base case from 50% window to wall ratio, and we want to reduce this number further. So we tested this on 40% window to wall ratio and 30% window to wall ratio. And we find that when we reduce the window to wall ratio to 30%, we still have enough daylight in this living area. So which gives us the confidence to reduce the window to wall ratio to 30%. And we keep the window to wall ratio to 30%, and we think that if we increase the ceiling height from 8 inches to 24 inches and make the window wider, so we are able to further increase the daylight environment in the living space. So in this project, we are able to reduce the window to wall ratio and still have a good daylight environment in the living space in the apartment unit. And these are some resources on the daylighting simulation. So the Ladybug Tours forum is a place that you can post questions when you are conducting your simulation. And if you are just getting started with Ladybug and Honeybee, and the YouTube channel of Chris Mackey is a good place to get you familiar with the Ladybug and Honeybee environment. And there is a GitHub page which has an article to explain the workflow of daylight simulation and some concepts on the daylight. And thank you. I'm happy to answer questions.
Awesome. Thanks, Mohan. Any questions? I mean, could you talk about how so you did just a part of a building for the example, right? So could you talk about how you would approach that maybe for like a whole building, or like why you'd have to break it up, like how you'd sort of approach it if somebody gave you like a multi-story high rise with all the rooms wrapping around?
So for this, I'm doing this on this floor. So for the whole building, I will build the model on each floor and do several simulations, and then I will calculate the weighted average of the result from each floor and get an average daylight autonomy from that.
Cool.
Is there any way, Bohan, to make this, to take exported geometry from Revit for a small area, say like the same sort of study area? Could you take, say, if we carefully exported this, this export settings such that all the glass went to a certain layer and all the mullions went to a layer, interior walls. Could we do that in a way that you didn't have to rebuild it in Rhino? I'm trying to find better, sort of workflow to not have to redo all this work.
Yeah, I can take that question. I think that the best successes we have for this type of model come from the general massing components. However, I have seen walls and window systems come in pretty clean into Rhino. I think there's some exploration to be done about what happens in Revit specifically to make the geometries closed and solid and come in perfectly in on a layer. But I do believe it's possible.
Yeah, like I'd almost say like for the interior surface, what would be really interesting would be if, and I've seen this through Dynamo, is that you can extract the solid version of a room object, like extruded. So if you could use that and use that to establish your test zones and ceilings, there's definitely some potential. But then you got to have a little those workarounds of like whatever you're using from Dynamo to extract those solids. Because Revit doesn't really like exporting room objects, but yeah.
Well, what will be interesting in the coming months is you've probably heard of Rhino Inside. Maybe you haven't. There's a new venture that McNeil and partners have done to allow Rhino and Honey and Grasshopper to run inside of a Revit environment as a separate process. So I'm curious as to how that might make this kind of thing easier. So I can send you some webinars that have been going around in the last month or two. But this is something that's very exciting to me because I know that, while Dynamo ostensibly has Honeybee and Ladybug, they've never really worked right in Dynamo, to my knowledge. And, clearly they work better in Grasshopper. And so I'm hoping, that there's a way to bring these two worlds together.
Yeah, I'm looking at the website for it. It looks pretty interesting. Seems like there's a lot
So I have a question. So if you had perforated glass in the mix, could you account for that in your daylight analysis?
Like,
How would you do that?
like a Brit dot pattern or something?
Yeah.
Yeah, I've done that before with a frit. Similar to the surface geometry that is creating the window frame, you can add three-dimensional solid geometry for that frit pattern. So if you had a two-dimensional CAD drawing, you can extrude it into 3D and add it as part of the opaque solids and give it a material. And then, of course, the light will sort of go through it. Now, whether or not you're going to see that result impact will have everything to do on the grid size of your sampling and the quality of your output with the script. Because if those things are very, very tiny, let's say a 1/4-inch diameter dot, that might just fall off the table in terms of the range of scope that we're looking at for the 1/2 meter by 1/2 meter sample area.
I'm just thinking of the Desmond question in Cambridge side. He wanted to do different variations of frit and see the impact of the daylight analysis. So that's why I asked.
Right, and I worked on that project specifically, and we achieved that with a daylighting simulation, a different version than this, a very much earlier version.
But couldn't you also just get like a general number for the transmittance or like the values of what like fritted glass, what this percentage fritting is, and then you could just set your glass to that instead of even modeling all of it, right? Like you can modify like where it says reflectance and transmittance, what Bohan is showing. You can really just tweak that for fritted glass, right? And then that could be
good. I would say it's easier if we just doing this calculation before we work in the Grasshopper. We just need to calculate this number, what that transmittance is from the perforated glass. So we don't need to model that detail in the Rhino.
Right.
I would agree.
The likelihood that one of those dots actually hits one of your sample points is pretty low. So yeah, so I agree. It's probably just setting a number right.
Yeah, in the example that Josh was describing on the other project, the frit pattern was as such that as it moved up the building, the percentage of frit changed in a transitional gradient, complete gradient. So by applying a transmittance value to the entire glass plane, wouldn't account for that gradient change vertically. So you might have to split it into multiple panels of glass, which again would be a hard stop at each transmittance value. So to get really accurate results, we did model that in 3D and tried to find the perfect percentage of opening from the bottom most open gradient to the top most dense gradient, and what that did to, again, the daylighting on the floor surface inside this entry lobby. So depending on the complexity of your frit pattern and what it's trying to achieve, might require some more manual creative solutions in Rhino and Grasshopper.
Exactly.
So were all the dots the same opacity, or was it just the size and the spacing that made the more transmittance, or did the actual transparency of the dots change?
It was the density going up.
Same dot, same frit, just the density of the dot pattern vertically.
So it's a little more manageable. It's still unmanageable.
Well, we had to use a script just to achieve that gradient dot pattern, for example. To achieve a full gradient from top to bottom is very difficult in other software platforms. So even to derive the patterning, we turned to Grasshopper to do that for us.
So how long did it take to, like, you had to crank up your grid size, right? Like super, super small, right?
Yeah, we're looking at a very small area. I think like one of these hot zones that Bohan is showing on screen. So it was a much smaller footprint, a very focused model of just the entry canopy, very similar to being a rebuilt scenario like this. I believe it was from Revit as well that we brought the model. And yeah, we cranked up the resolution. We built, I think, everything down to about, I want to say the 1/4 inch, if not less than that, for the frit pattern. But it took about, let's say, the design modeling, right? Like all these stuff to prep the model. It took a few days. It took a little while for the designers to transition the models they had been designing with into something that was simulation ready, nice and clean, nice and tidy. Like Bohan described, it's a representation, a simplified version of your building geometry. And then the actual simulation work probably took about a few hours to run the different patterning options through it, and then to be able to compare them in the analysis and put some drawings together to show the client or show the design team. So it's a very swift process once the setup is there. Similar to most things, I guess, sometimes.
Hey, Bohan. This was really great presentation. Good job on that. I'm not sure if you mentioned this. I might have missed it because there's so much information. But does this account for the height of the floor within the building? And add to that, if they're building like complex buildings around the windows outside, does that, can you work that into your calculations?
Sorry, you're asking the.
Well, there are two parts. So if your floor is on a low level, then presumably you'll get less light than on a high level, and that might be a result of context buildings that are surrounding the study building.
Yeah, so if you have a context building, you can build that geometry and input into Rhino, and also you can plug that into this component called context surfaces. So this will take that into account. And normally, so in terms of the height, normally what I will do is I will import this DWG file from the AutoCAD, and when I import it, I will raise the height of this to be the actual floor height, and I build the building geometry based on this DWG file, so that the geometry is the same height as the real building.
That's right.
Cool.
Yeah, I do the same thing in the Z and getting the building up to the right height. And also, I think it's important to know, I asked that same question, Christina. I was like, well, what about the context? And what about the building that's right next door? I think the answer I was given is that for LEED, you actually don't have to include the surrounding context. If I'm wrong, Kristen and Bohan are going to have me like on a stick, but I'm pretty sure that's the answer I got, which is you don't need to calculate it for LEED.
This is directly related to the project that I'm working on with Genevieve, who's also on the call. We're trying to study the impact of our proposed buildings on some condo owners living nearby, and we want to know impact to views, but I guess impact to access to sunlight would be also important. We want to know how far our buildings have to be before their living room gets cast in shadow. So it'd be an interesting study for us to do together.
Definitely. And I should point out that the scripts and the things that we're trying to build as a team and share with everyone are, you know, maybe there's a way that you can go back through this entire video and do it step by step by yourself. Chances are that's going to be pretty challenging the first time. So reach out to me, reach out to Bohan or Anish or Kristen Fritsch, and we'll get you the support side by side to help through this process. That's also what we're here for and available for. And when you talked about a view study, I have a separate script that's all about view corridors and obstructing them or keeping them open. It's very graphic and beautiful. So if you shoot me an email, I can set you up with that one. I think that one is super easy to use, especially with someone like your experience, Christine.
Yeah, also,
Nice.
also for Christine's question, so if there are context buildings near our project, I think it is to see how that affects daylight. It have a bigger impact on the views. So when we were doing the view for the lead or for well, so we do consider these context buildings, and to make sure that they are not blocking much view from our from our interior. So LEED has a requirement on this, within which distance that you should not have that context building that block your view. So I think this is something maybe related to that.
Well, we'll coordinate offline on this. It's not urgent.
Sounds good. To see some of those scripts and more, you can always head over to Emmy. There's a Grasshopper definitions library there. You can always head to the recorded sessions and the resources that we've been building for the Grasshopper work group. And of course, let us know if there are topics or project work or some crazy idea you have about using Grasshopper and Rhino together to influence architecture and design. We're all ears, and we can start to even structure some of these calls and work sessions towards specific problems that you're interested in or specific ideas. So keep us in the loop.
I will forward the Rhino Inside webinars to anybody. I'll forward them to Anish and Tom, and you guys can distribute them to anybody else that's interested. That's something that's becoming more important in the next month or two. A lot of people are sort of excited about it, so I think it could be a great way to bring these sort of realms together.
Yeah, and that's the big thing, right? When Tom was saying that, like, in his project, 3/4 of the time is really spent on translating all the geometry. But part of this whole idea is that if you see what you can do at the end with good geometry, there's an incentive to, make good geometry from the very beginning. I think is really one of the big things, is that you want on your projects to, like, advocate for everyone to be making good geometry that's categorized and layered and, fully solid. Even if someone is like, oh, in SketchUp, I can just paper over walls and just get through the day, right? People just do these models to get through the day. But if you hold yourself to a little bit of a higher standard, you can save yourself a lot more time down the line. and take advantage of a lot of these really powerful design tools. So
Yeah,
Yeah, and
people know what the opportunities are and they know what the rules are. You know, we can always hope that they will eventually model with that in mind, knowing that that will save them time. If they're just going to sling the model at somebody else and let them worry about it, then there's less hope for that, especially for SketchUp users, SketchUp models, because it's usually more frantic, and it lets you get away with a lot more. But anyway, that's to be continued, and we'll be looking at this. You know, how can we save stuff out that that can maybe drop right into a study and be useful, separatable by category, so that you can select it and drop it into these nodes. And maybe Jackie and Bohan can work together a little bit. And I'll look over your shoulder. You could make
yeah, there's definitely opportunities to cross collaborate between our different areas of expertise and bridge those gaps that we're seeing. You know, we could go on and on about design workflow and the right software at the right point in a project. I don't think you're going to convince many of us, like with Anish and I, that we're going to transition our design workflows into Revit. I think our priority and preference is to educate in Rhino and Grasshopper. You will see some sessions coming out for Intro to Rhino, all the way through some pretty advanced like workshops in the same video tutorial. Joe Kyle and I are working on that with the fabrication team. So if you're interested in transitioning yourself from SketchUp into Rhino, if you're interested in using Rhino and Grasshopper as a design platform and using the geometry that you're developing and getting real-time feedback on data, which can really drive some decision-making from a logical point of view, you can certainly transition the geometry that's making sense and the geometry that's been approved, for example, and bring that into Revit for documentation purposes. We would never suggest documenting a building in Rhino and exporting hundreds of drawings, don't get me wrong. But we find that the greatest value in Revit is the documentation and organization of two-dimensional work, which is the drawing set, where Rhino is a repository for all the three-dimensional work and the data-driven design that's available today. So that's my own 2 cents, and I'm sure somebody else has a different opinion, of course.
Sounds good.
and also, sorry, so this is only the foundational components that in the data simulation, and you can also explore more functions. For example, if you are in the very early design stage, you don't know where you want to put the windows, you can use this component that can generate the window openings based on the facade. So in this way, you can just do a quick simulation and say what's the different window to wall ratio based on the facade. What will that impact your design, like in the very early stage?
That's great. And we're going to hear a lot more from Bohan as part of the high performance group. Thank you so much for being our first super user, spotlight, star, whatever we're going to keep calling the folks that want to share their hard work and extraordinary efforts. You know, teaching yourself how to make these tools, teaching yourself how to learn what data you're solving for and why, and then being able to get all of that and describe it in such a way. Kudos to you, and very well done. Appreciate it.
It's a very nice presentation, very well organized and easy to follow. Thank you, Bohan.
Thank you so much.
All right, I'll post the recording on Emmy. Thank you, everybody. Bye.